Understand the problem, make a plan, execute the plan, check your work. Sounds easy, can be more difficult than you think. So understanding the problem means reading the problem and understanding not just what it says, but what assumptions you can make. So if a problem says I have 2 pucks on an air hockey table, that means I can assume that friction is 0. I need to make a plan, and the plan is going to be sort of the big picture ideas that we're operating under. So when I read a problem and it says I have a skier going down a hill and he drops his backpack and jumps off the end of a ski jump, how far does he land? I go, okay, well, I know I need to use conservation of energy, conservation of momentum, and kinematics from the perspective of projectile motion. So all of those are my plans, and then to execute that plan, I have to use the tools that are associated with each one of those plans. So conservation of momentum, I have to know that momentum is mv and a variety of other things. Conservation of energy, I need to know that I'm using the work energy theorem. And then check your work just means try to solve the problem in 2 different ways if you have time, or at least understand that my problem should make physical sense. So if I find that I'm throwing a ball at 100 meters per second, I go, that's probably not right because that would break my arm. Or if I see that an ant travels 45 kilometers in 22 seconds, I can say, oop, that's probably wrong too. Maybe I've made a mistake in one of my equations or the units that I'm using. So again, the plans of the big picture gives us the framework and assumptions that we're working under, and we can use them together sometimes. And they have these associated tools and equations. And I think there are probably only 7 or so plans from the first semester, and we'll be continuing to use most of these in the second semester. So in the first semester, we talked about Newton's first law and second law. Those are big picture ideas. Kinematics, rotational motion, which is sort of those first 3 ideas in their rotational form, conservation of energy, conservation of momentum, and fluid dynamics. So if I want to talk about Newton's first and second law, you can see that Newton's first law says that the sum of the forces is 0, so that's a static situation. Newton's second law says the sum of all the forces is equal to ma. And in that case, I have a net force. So after I add all the forces up, I still have something left over, and that means that I have an acceleration in motion. I can have motion in Newton's first law, but I can't have changes in direction or changes in speed. So the ideas that are used for both of these concepts are vector addition, so this guy, and trigonometry, and oftentimes we might say something like ax equals a cosine theta, and free body diagram. So maybe if I have an object on an incline, I can think about the weight going down the ramp, the weight going into the ramp, the normal force, and the frictional force. In Newton's second law, I also have these ideas of what is velocity and what is acceleration, and I have these definitions here. So velocity is the rate of change of the displacement, acceleration is the rate of change of the acceleration, and remember that this is my vector notation. Kinematics is oftentimes used with Newton's second law and some of these other ideas, and they're just equations that allow us to go from something like Newton's second law that says F equals ma to get a distance out of it. So if we remember correctly, and I'm breaking this into components, I can say things like the change in displacement is equal to the initial velocity in that direction times time plus a half the acceleration in that direction times time squared. The change in velocity in a particular direction is equal to the acceleration in that direction times time. And then I have one equation that eliminates time, and I can say that the final velocity squared minus the initial velocity squared is equal to 2a delta x. And all of these equations are using the assumption that a is a constant. And another big picture idea that we use this under is in projectile motion. And free fall. So next we have rotational motion, which is just these earlier ideas and a few later in their rotational form. So the kinematic equations still hold. We just replace x with theta, v with omega, and a with alpha. And then we have two different accelerations that can be present. So one is a tangential acceleration that increases the angular velocity, and one is the radial acceleration, which is equal to v squared over r, omega squared r. So when I'm talking about uniform motion, this is the equation I'm using, and I know that when I have uniform circular motion, that the sum of all the forces is equal to this radial component of the acceleration, which is mv squared over r. I also have Newton's second law in angular form, which says that the sum of all the torques is equal to I omega, and I is just the angular mass, right? And then I have an angular kinetic energy, which is 1/2 I omega squared. Conservation of energy is a very important tool that we've talked about, and that says that work is neither created nor destroyed. Energy is neither created nor destroyed, but it's actually converted from one form to another through work. And work is just the force in the direction of motion times the motion, or F dot D. And we can write that as F D cosine theta, where theta is the angle between the force and the displacement. Then we have the work energy theorem, which says that the work done by non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. And kinetic energy is just that energy due to motion. So it's 1/2 mv squared, and if I have rotational motion, 1/2 I omega squared. Then I have the change in potential energy, and all conservative forces have an associated potential energy. So if I have weight, which is mg, its associated potential energy is mgh. If I have a force for the universal gravitational force, which was gmm over r squared, its potential is negative gmm over r. And then for my Hooke's law force, which was kx with a minus sign because it's a restoring force, I have an associated elastic potential, which is 1/2 kx squared. Conservation of momentum, I have the impulse momentum theorem, and I have to remember what momentum is, which is just a vector in the direction of m times v. And from this momentum impulse theorem, I can see how Newton's second law was originally formulated. So delta p over delta t, so this is just second law. And if I have no external forces, that means that delta p has to equal 0. So I have this conserved momentum quantity, which has to be conserved in both magnitude and direction. And this is oftentimes used when we talk about collisions and explosions. And last, we have fluid mechanics. And we're not going to use a lot of fluid mechanics ideas in this semester, but just to refresh your memory, we have things like the buoyant force, which says the density of the fluid times the volume displaced times g is an upward force on an object. We have Pascal's principle that says that pressure is distributed and travels through an entire fluid, which says the pressure in has to equal the pressure out, and that's this guy, and it's how things like hydraulic jacks work. And then we have Bernoulli's equation and the continuity equation, which are used for fluid dynamics, the earlier ideas being applicable both to dynamics and statics. And in this case, I have the initial pressure plus 1/2 rho v squared plus rho gh is equal to a constant. That looks a lot like conservation of energy, by the way. And then I have the continuity equation that says the area, cross-sectional area of the fluid moving times its velocity is the same no matter where I look at it, which just means the amount of water in has to equal the amount of water out. So if there are any other ideas you'd like me to make videos on, please tell me. I know I brushed over vector addition, and that can be really tricky for people, so if you want me to refresh that, feel free to ask, and if you have any other questions, feel free to ask. Thank you.